So as I just mentioned, our topic of the day is the electrical transformer.
I'm just curious if, for like the magnetic couple stuff, are we able to make a bicycle?
Yes, I haven't done it a whole heck of a lot, but there's definitely a transformer. Yeah. So one of the things actually that we're going to be learning about today will be able to be applied to some of the topologies that I gave you, where we are going to learn about equivalent circuits for transformers, which are just a specialized type of magnetically coupled pair of coils. All right, so transformers. So let's consider two magnetically coupled systems. So I'm going to start and I am going to wrap a coil of wire around this coil. Once again, exactly like a solenoidal inductor. Like so, we're going to have this coil, which will have a voltage V1 of T and a current I1 of T, like so. Bottom of this guy. Let's call this and this current I2 of T, like so. Two coils that are purposefully placed so close together. In fact, they're wrapped around the same cylindrical core. So explicit or intentional mutual induction between the two coils, we have formed a transformer, right? So in a solenoidal case like this, let's say that coil 1 is the one that's carrying a current. We're going to have a magnetic flux density or B field lines like so that wind up, passing through or coupling both sets of coils so that number 2, or if coil number 2 is, we'll also see some amount of current flowing through there. Now, this particularly, right? So at the ends of the transformer, flux coming out and bypassing the coils, which doesn't really help things out because we're losing energy as flux escapes the coil. So instead of having a single rod as our core, we might have also be done as a torus, but that will take me too long to draw in 3 dimensions. So we have this rectangular core. We could wrap our primary coil around one leg of this core. I1 of t. And we would wrap another coil around another one of the legs. It doesn't particularly matter which leg we use. And just for the sake of argument, I'm going to put this current flowing out. This coil has N1 turns, this coil has N2 turns, this coil has a that is made of a ferromagnetic material. Ferromagnetic materials tend to enhance magnetic flux density or B fields. And so what we'll wind up having is a magnetic flux that is confined one coil passes through the second coil, and we have very, very strong coupling. And we'll talk about that here in just a moment. Off, giving you access to different voltages. So we have a solenoidal angular core transformer over here, and out these when you get into your electric machinery course, if you choose to take that class at the beginning of your senior year. You'll flux, excuse me, I said flux density, flux linkage as if it were a voltage. Magnetic flux plays the role of current, and the reluctance of the different parts of your core play the role of resistance. But anyway, that's for a later class. Yes, Nathaniel. You what now? So that is a great question. So there are things like three-phase transformers that are one big unit where you're effectively transforming a and then stepping that down to, say, the transformers outside of this building are. There are that are three single-phase transformers, and where they get used is if you need three different voltages, right? So a three-phase transformer is going to give you put the same voltage at the input, you're going to get the same voltage at the output. Whereas if you do it phase by phase, you can put in a transformer that gives you any probably on class on Friday when we talk about ideal transformers and all that kind of good stuff. So the short answer is it depends on the application. But there are single phase transformers drive around town and go near like a new building or apartment complex and you see a big green box on the ground, that's usually a three-phase. Because I chose to. That's it. Yeah, so I'll just arbitrarily here. So we haven't worried too much about dots or anything like that. I mean, realistically, the way that this flux is going, I think the current, based on my right-hand rule, it should be coming out this way anyway. But we handle all of that with the notation when we get into the circuit and analysis type of things anyway. Choosing to use a ferromagnetic core and this particular geometry in order to ensure coupling between the two coils is going to be. So we can quantify that coupling by a coupling coefficient. So the coupling coefficient A So when K ranges from 0 to 1/2, we call this a loosely coupled coil. And the solenoidal transformer, like we have on the left-hand side here, would like geometry. Okay. When K ranges from 0.5 to a little bit less than 1, we call this a tightly coupled coil. It would be a structure like this on the right with a small air gap somewhere in it. So we could actually cut out a little slice of this core material, leaving behind an air gap, and we'll still see that the overwhelming majority of the flux makes it through this magnetic path. But in that air gap, we're going to see it kind of spread out, and we might lose a little bit of flux there. Okay. You might be asking yourself, why the hell would we ever introduce an air gap? And all that kind of good stuff, is that an electric motor, particularly an induction motor, can be thought of as a structure. We just put a small air gap on top and a small air gap on bottom to minimize the loss of flux. So the model for are practically the exact same thing. It's just the parameters are slightly different because one has air gaps and the other doesn't. Is when K is exactly equal. And when K is exactly equal to coils. So the value of our coupling coefficient K material the core is made of, as well as the inductance of the coils themselves. Definition for our coupling coefficient is going to be our mutual inductance M divided by the square root of L1 times L2. Okay. Now, one thing that I want to point out here is that this definition for our coupling coefficient K is dependent on the value of the mutual inductance and the value of the self-inductances expressed in henries. Just put those impedances there and it'll work out the exact same way, because the impedance of the mutual inductance is going to be J omega M. The impedance of the self-inductance L1 is going to be J omega L1. The impedance of we're going to have a factor of the square root of J omega squared, and they wind up canceling each other out. So you don't actually need to take things back to in there, and the equation will work just as well. So just to save you guys a little unnecessary math down the line. Okay. What would the relationship between the mutual inductance and the self-inductances be? Well, hopefully that's fairly straightforward. If K is equal to 1, then M must be equal to the K is equal to 1. So if I tell you that we have a perfectly coupled coil or pair of coils in our system, I don't need to give you any other information other than the dots. You should be able to figure out everything else and analyze the circuit. All right, so decide if I want to work an example problem now. No, not yet. We'll do it in a minute. All right, so in addition to the two coupled coils that we have, a physical transformer or practical transformer also usually includes some amount of resistance in its model, right? So voltage phasor. This set of terminals is the start of my transformer. This is the self-inductance of the primary, and let's put a dot here. Here's the self-inductance of my secondary, L2. The resistance of my secondary, R2. And then I'm going so everything between these red dashed lines is my transformer. Okay. Just a moment here. I do want to explicitly draw either piece of information will allow you to calculate the other piece of information. And then and this portion of the transformer is practical transformers. It literally does not matter which side you consider the primary and which side you consider the secondary. It's just hooking up a voltage to one side and then a load to the other side. And whichever side the voltage is hooked up to, consider it the primary. Whatever side the load is hooked up to, consider it the secondary. Standpoint of our voltage source Vs, what does it see? Just some impedance, right? Depending on what the parameter value. The values for R1 and R2, those are just representing the copper losses in those particular portions of the some amount of resistance that causes us to lose energy loss with resistors here. Okay, nothing fancy or crazy going on there. So how are we going to figure out what the impedance seen by our source voltage is? Okay, so let's define some mesh currents here really quickly. I'm going to define them so that they are flowing into the dotted terminal in each case. So let's call this mesh current I1. Let's call this mesh current I2, like so. If we write a KVL loop around the primary, we would have negative omega L1 times I1 plus J omega. Be okay with this expression? Anybody have any questions about where any of these terms came from? Right, so we're just looking at effectively the induced voltage. Some voltage drop associated with our self-inductance term, some voltage drop associated with our mutual inductance term. Right? We are going to have R2 L2 times I2 J omega M times I1 what we're going to do now is we're going to do a little bit of algebra here, and we're going to see if we can express the current I2 in terms of the current I1. Right? So, should would be equal to negative J omega M divided by R2 plus J omega L2 plus ZL, this whole fraction multiplied by I1. So I simply move this guy to the other side and then divided through by this impedance. If I substitute this relationship in for I2, is Vs is equal to R1 plus J omega L times J omega M times I2, where I2 is negative J omega M over R2 plus J omega L2 plus we're going to have R1 plus J omega 1. So what happens when I multiply J omega M times negative J omega? What's squared? So I'm going to have negative J squared, which is what? Positive 1. And then I'm going to have omega squared times M squared. So it's just going to look like plus omega squared M J omega L2 plus ZL right? So the input impedance is just going to be the ratio of our source voltage divided by our mesh current I1 because it's the current leaving the positive polarity terminal of our source voltage. And so that's going to give us R1 plus J omega L1 plus by R2 plus J omega L2 plus our impedance ZL. And this second term is the reflected secondary loop impedance. So secondary referred to the primary side of the transformer, okay? When we talk about reflection coefficient purely in terms of the turns ratio of the transformer. So we can refer things back and forth only depending on the turns of the coils and not having to worry too much about the other characteristics. That's one of the benefits of looking at things like an ideal transformer. But for right now, we're sticking with a practical model. All right, so we have gone through here and for a simple transformer, derived a relationship for the analysis in particular. We can use this input impedance model in order to which means I can ask you a question. Don't actually have to have a computer to solve the damn thing. Okay, so let's look at an example. So this is a similar we have a 120 angle 30 degrees volt source. These will be the terminals of my transformer for what it's worth. And then I'm going to have an impedance here of 3 ohms in series with negative J2 ohms. Here, let's put a J. Let's define our here is my secondary coil. Let's put dot on bottom, J20. Six ohms, my terminals, as it were, for my secondary of my transformer, and then my load. Let's define my mesh current I2. Obviously, my currents are both flowing into the dotted terminals so that everything is supposed to wind up getting a positive sign, okay? So I'm defining these mesh currents. Let me close my email client. Apply the equation that we used earlier. Now you might be thinking to yourself, but the dots are on the different side. Oh. Okay. The dots are on the different side. Don't I need to change anything? Not really, right? So this is just a series combination of elements. So if I flip this whole thing upside down to put the dot on top, what would change? Absolutely nothing, right? So that's why I don't really care. Okay, as long as I define my current so that they're flowing into the positive, or excuse me, the dotted terminal, everything's going to work out okay. All right. So if my goal here is to determine the power, let's say average power, because it's particular circuit, I do what we did in class on Monday. And all that kind of step of input impedance transformer system, I can avoid actually setting up that system of equations, right? Transformer B. Well, I should have, and then I should have a term for my reflected secondary loop impedance, right? What should my primary loop impedance be? Anybody have any thoughts? 3 plus J3. 3 ohms. Okay, I agree with that wholeheartedly. What about my secondary, reflected secondary loop impedance? Down there on the bottom. Times m squared. What's that? Negative omega squared 4 ohms. Okay. This 2 ohms is J times. So I believe personally that omega m is omega m squared is just 2 ohms squared. We okay with that? Yeah. Impedances work? So if we throw this into (4.2) angle 2.181 degrees. Oh, in rectangular 2 plus 2.820 ohms. Into the equation that we derived a moment ago. All right. How are we going to use this? Well, I would argue that right. So I know now one by 2 mesh currents without actually having to use a computer for anything. So my mesh current I1 that impede a thing. So 120 angle 30 degrees volts divided by 4.2 angle 42.181 degrees ohms. With an angle of negative 12.181 degrees amps. Things get slightly difficult only from a thinking about things perspective. I know what I1 is. How do I use I1 to find I2? Because I'm going to need to know I2 to get the power I'm interested in. Right? So in class, we were able to write the KVL equation that included the effect term is multiplied by this. Everything that's in that equation except for I2. So that's what we're going to do here. So if we write a KVL equation around our primary loop, we are going to wind up getting 120 angle 30 degrees volts is equal to 3 plus J3 ohms times I1 plus J2 ohms times I2. Right? Everybody okay with where that equation came from? Literally just KVL around the primary. We can algebraically rearrange this to find I2 pretty easily, right? So I2 is just going to be 120 angle 30 degrees volts minus 3 plus J3 ohms times I1, where I1 was 28.571 angle negative 12.181 degrees. Going to be divided by J2 ohms. And so this will be equal to 3.029 with an angle of negative 16. Now I have I2. How do I find the power absorbed by the 4 ohm resistor? Okay, so this is an AC circuit. Is it I squared R? Number, I'm going to screw some things up. It should be I times the conjugate of I times R, but there's also a slight error in there as well. Okay, so let me write some things down here. Okay, so P 4 ohms, we are saying that it is going to be I conjugate times I times R, which is going to be the exact same thing as the magnitude of I2 in this case squared times R. What are we forgetting? What was that? 1/2. Why? You're right, but why? RMS phasor voltages and currents. We weren't. We were just using our regular phasor voltages and currents. So in order to fix this, we literally just need to multiply by a factor of 1/2 to put things in terms of the R. So that's going to look like 0.5 times 3 amps squared times 4 ohms. And because when I originally did this example problem, I was only interested in calculating I and not the power, I'm going to have to use my phone to do this math real quick. 0.5 times 3.029 times 3.029 times 4 looks like 18.35. So very similar to a problem that we would have worked on Monday, but now we no longer. Let's take some time now and look at equivalent circuits for transformers, okay? So effectively, going back to what Gabriel was asking me earlier, is there a way to put these magnetically coupled circuits into LT Spice? I believe there is a way to do it as they are. I don't know what that is, but once you learn these equivalent circuits, you can do it because it's only going to be in terms of inductances, right? You're not going to have to worry about any coupling. Okay. So let's look at things here. How did it scroll that far? So transformer equivalent circuits. So let's say that I have a transformer, and I'm going to explicitly label this terminal as A. Let's explicitly label this guy down here as B. This is my phasor voltage V1. This is my phasor current I1. This is my self-inductance L1. Here's my self-inductance L2. Let's call this terminal C. And this terminal D. This will be my phasor voltage V2. This is my direction for current I2. Here's my mutual inductance. Okay. So I'm also going to add something else here. So this is optional, meaning that it's not required, but it will help us think about things here in a moment. We're tied together at the same point. That does not have to be true. They can be separate coils, but our equivalent circuit is going to wind up tying these guys together. We have two different options, okay? So our first one is what's called the T equivalent circuit, and you'll see why in just a moment. So here is terminal A. We're going to have an inductance L sub Y. and inductance L sub Z. Terminal D. Here's terminal C. Here is our voltage V1, our voltage V2, I2. This inductance L sub X is equal to minus M, and the inductance sub Z is just equal to M. Okay. And just to be clear here, this is our
No longer magnetic.
right. So we're throwing away the magnetic coupling. It's being taken into account by our expression. Caveat, if the direction of either of these currents are changed, meaning that we don't have current flowing into the dotted terminal on both sides, we do have to fix something. And that fix will literally be change the sign on it. I'll explicitly write that down in a moment. Okay. Right, so the equivalent circuit should not have a dot because it's all taken care of with the arrangement of the elements and the equations for the elements. So all of the dot and is the current flowing into the dot or not dot is all taken care of with these expressions. The only thing we have to pay attention to is if either of these currents are flowing in the opposite direction as we have documented here, change the sign on it. And I'll write that down in a moment because the exact same rule applies to the second equivalent circuit that we're going to deal with. And I only want to write it down once because I'm lazy. All right, so this is our T equivalent circuit. Now we're going to develop our I equivalent circuit. So here is our terminal A. Too far with that line, my apologies. So we're going to call this inductance LC. We're going to have another inductance down. This one will be LA. Over here is our terminal C. Tie all this bottom stuff together. Over here is terminal D. Here is our voltage V1, our current I1, our voltage V2, and our current minus M squared divided by L1 minus M. The inductance LB is L1, L2 minus M squared divided by L2 minus M. And the inductance LC is L1, L2. Now I will write our note. If into an undotted terminal, replace M so those are our rules. So that would make LX, L1, L2 plus M, LZ negative M. For these guys down here, the numerator is going to stay the same because we're squaring it, so the negative sign doesn't do anything, but the denominator is going to change. I'm going to stop here and we'll work some example problems. Use these equivalent circuits to aid in our circuit analysis at the beginning of class on Friday.